Namaskar, my dear friends. So we have already seen the overview of this particular microcontroller PIC16F18877. Okay. So our target device is 40-pin PDIP package. So we will be seeing only this particular microcontroller. During the device overview, we have seen the features and using the data sheet, what are the different details. Now we'll try to understand how we can design the schematic directly. All right. So let us move. We have this pin description. You can see there are 40 pins, 1 to 20 and 21 to 40. All right. So this is the pin that has been organized. I have already discussed what are the pins functionalities like VDD, VSS are power pins, ICSP data and ICSP clock are programming pins. It has 5 ports: port A, port B, port C and port D and E, right? So let us see the outline that we will see in this particular session. First of all, we'll try to understand how we can design the power supply. All right. So power supply, then we'll see the programming, we'll see the resetting the device, how we can interface some push buttons, some dip switches, some LEDs. LEDs we'll try to see 2-3 methods, how we can connect an LEDs to indicate some indications. Okay. We'll also try to understand how we can interface I2C communication, SPI communication, UART communication. We'll be seeing PSP as well, like parallel port, serial parallel serial port. Okay, so basically we will be seeing data communication. Okay, so this will be used in, let's say, LCD interface. Okay, or you have to send some data in 8-bit, so that is called uh, PSP bus. Okay. Same way LCD interface, as I already told you. Then we'll see timers, we'll see PWMs generation as well. Okay. So hope you guys are clear with the topics that we are going to see in this session. Let us directly dive into the microcontroller. So as you can see, we have PIC16F18877-I/P. So this is 40 pin PDIP package. Okay. And I have not changed the pin numbers. It is just 1 to 20 and 21 to 40, all are as it is. I have just named little bit more like oscillator instead of just having RA6, RA7 and all. I have put some more details about the pin names. Okay. Now, very first thing, what do we need? What do we need is we need to have power supply VDD. So VDD, you can see there is a 0.1 microfarad capacitor which is acting as a decoupling capacitor. So your aim is to put C61, that is 0.1 microfarad capacitor, as close as possible to the pin number 10 and 11. Okay, I'm sorry, 11 and 12. Similar to that, one more decoupling capacitor will come here, which will be uh, which will be C62. All right. So C62 will be coming at the pin number 32 and 31. Got it? So this is first thing. I'll tell you VDD will be working with 5 volts. So VDD will be working as 5-volt supply. If you want, you can have LF series, which will be working at 3.3 volt as well. I will give you that at last. All right. Next is we have to have a programming connector. So programming, you can see we have 6-pin connector that will be acting as a ICSP programming or ICD programming. Okay, ICSP programming or ICD 3, ICD 4, all like can be applicable to this particular programming connector. Even PIC-Kit 3 is also applicable. So what is the first pin? MCLR, which is going to be reset connector. Then pin number 2 is your 5 volt, which is going to be the VDD. Okay, so if you want, you can rename it as VDD. Got it? Pin number 3 is your ground. Pin number 4 is your ICSP data. So you can see ICSP data is here, and ICSP clock is pin number 5. So ICSP clock is pin number 5. If you want, you can leave pin number 6. You don't have to connect it, or otherwise earlier it was coming as like P, PGD. There was something called PG programming. So PGD, PGC and PGM. Okay, so PGM was used earlier, but now they are not using. So D was for data, C was for clock, and M was for like management, something like that was there. So so PGM you can leave it blank. So you don't have to connect RB3. So RB3 you can utilize it for some other purpose. Got it? So pin number 36 and be used for you some other application. Understood? So you have understood how to connect your decoupling capacitor, how to connect your programming connector. Then let us see how we can reset the particular microcontroller. So to reset the microcontroller, you have to have a like a pull-up resistor with VDD. So 10K I have put here with VDD, and as soon as you press this particular push button, it will get grounded. Got it? And this is how it will get reset. So reset connector you can connect directly with a simple push button switch. So I will give you the part number as well for this. This is taken from Worth Electronics. Very good part number, which is very low cost as well as very high, uh, like reliability. Next, I have utilized one external oscillator as well. So this is a crystal oscillator of 12 megahertz. You can go up to 20 megahertz oscillator, okay, or even 36 megahertz. So I will request you to, or I'll suggest you to give a oscillator of 20 megahertz, or like as low as 8 megahertz you will also be fine for you, okay. Because you will not be working more than, let's say, 4 megahertz application or 8 megahertz application. So 8 megahertz oscillator is also applicable, but I have taken a very reliable good one which is around 12 megahertz application. Got it? So you can see oscillator 1 and oscillator 2 have been connected to this oscillator pins. If you do not want to use an external oscillator, you have internal clock source, so you can utilize that one. Got it? Next, I have put RF5. So RF5 is here, this pin, and this pin is acting as a like ADC. So simple ADC connection I have given with a potentiometer. This is my pot. Okay, so potentiometer of 10 kilo ohm. It is taking, as you move it, the voltage level will change at this point, and accordingly the ADC value will change. So this is very simple ADC interfacing. If you want, you can utilize this as well. Got it? Rest other pins I have just renamed, and I will try to utilize them as a different connections. Let's say RA0, RA1, RA2, RA3, all these things have been renamed. And we have SCL connection here, like this is my I2C connection, clock connection, and this is my I2C data connection. Okay. All right. So let us move next. Very first thing, what do we need? We need my VDD, right? We need my power. So for that power, let us try to understand how we can give power to my microcontroller. So let us say you have a connector which is like taking a VCC and which is giving let's say 12 volt. So 12 volt you can connect here, and what will happen? 12 volt to 5 volt connector I have given here. So this is my converter. All right. So this converter, what it will do is it will convert from your V input to your V output, and V output will be 5 volt. Okay. One more option I have given is port. Okay. So this is jack. Basically these days, like a lot of adapters comes. Okay, like 6 volt adapters, or like 9 volt adapters, 12 volt adapters. Let's say 12 volt 1 ampere or 2 ampere adapter is more than enough. Okay. So if you connect this, then this will directly come here, and it will convert again to 5 volt. So any one of these two you can utilize. Sometimes what happens is you are not giving like 12 volt or something, you are giving 5 volt directly. So instead of using your regulator, you can directly feed this 5 volt to your VDD. So what I have done is you can remove this D9 so that this connection will be disconnected, and VCC directly I have connected through a resistor. Okay. So these two resistors are a little bit high, big resistor, let's say 0805 package, or if you want to increase the rating, you can go up to 1206 as well. Okay. So this VCC directly will get converted to VDD, and VDD will be connected to all the points. Got it? I have connected here 10 microfarad, so there will not be a requirement of bulk capacitor near the microcontroller. So microcontroller only decoupling capacitor will be more than enough. Got it? Now, if you need a 3.3 volt for some other applications inside the circuit, I have given one TPS 7A2033. So this is around 300 milliampere, or I think 20, yeah. So 300 milliampere rating regulator. So from VDD, that is 5 volt to 3.3 volt converter. This is very good converter. Okay, and this is very new IC from Texas Instruments. If you want, you can utilize some other uh, 5 volt converter as well. There are a lot of other converters. Okay, so I have given you those part numbers in my previous videos as well. So hope you guys are clear about the power supply methodology. Okay, what is the first step? What is your power available? So let's say you have 12 volt available. 12 volt to 5 volt, you can put one a linear regulator, which is like a very easily available these days. Okay, so 12 volt to 5 volt, or even like 9 volt to 12 volt is 9 volt to 5 volt is enough. If you want to have like no loss or something, then you can go for switching regulator, that I can take up a separate session for those things. Okay. Got it? So VDD is clear and the programming is clear. The resetting of the device is clear. We have already connected one external oscillator. All right, and how we can give the power, that we have completed. Got it? Now let us see some very regular, very popular, interfaces that we generally use in our circuits. Okay. So basically, what is the first step? First step is to connect a push button. Okay. So what I have done is I have taken this 5 volt. Okay, that was VDD. So I will tell you how VDD was converted to 5 volt. There was a resistor in the middle, and this VDD has been renamed to 5 volt. So it is easier for me to understand. It is 5 volt or 3.3 volt. Okay. Now I have taken one 100 kilo ohm, and then it is going to user PB. Okay, 0. So user push button 0 is going here, and through a 0 ohm resistor it is going to RB 0. So you can see, let me tell you, RB 0, RB 0 is here. Okay, so this is interrupt pin also. Okay, so what happened? Directly you can read this particular user push button 0 at your RB 0. Understood? Similarly, user PB1, this push button, okay, will be read at RB1. So what will happen? Let us say this push button is not pressed. Okay, so this user PB1 will be read as high. Okay, and as soon as you press this, so it will get grounded. So user push button 1 will go down. Okay, so as soon as you see a low on the microcontroller, you will understand the push button has been pressed, and you will act accordingly whatever you need. Okay, another method is I have dip switches. So I have 4 switches here. Okay, so if you push it at right side, it will get disconnected. If you push it at, sorry, if you push it at left side, it will get disconnected. If you push it at right side, it will get disconnected. Okay, so sorry, left side, what will happen? This will get connected to 5 volt, and right side, what will happen? It will get disconnected. It is written open. All right, so in this what will happen? Let us say you have to set these pins to 0 1 0, something like that. Okay, so dip switch 0 1 2 3. Let us say all of them are at left side, so all of them are actually 0, they are grounded. All right, so all these 4 pins at RD0, RD1, RD2, RD3 will be read as 0. Okay, now suppose you want to set RD0 as 1. Okay, so what will happen? You put this pin number 1 and 8, that slider, like this. Okay, so this 5 volt will go here. Okay, so it means RD0 will become 1, so it will become 1 0 0 0. Understood? So this is the setting that you can do for your microcontroller pins. Any doubt here? All right. So we have understood how we can connect push buttons, how we can connect dip switches. Based on our understanding, we can set their values as well, whether we want 0 or 1, based on the sliding switch. All right. And I have given the part number of these things. Okay. So these things, if you really require, like what is the exact part number or something like that, something like that, you can always put your comments in the comment box, and I shall be able to give you the exact numbers. Now, very important thing is LED connection. So I have separately made one small videos with LED connection. having different methodology. So here a very simple thing, you have 5 volt here. So through one small resistor, it is going to the LEDs, and it is going to user LED 0. So what will happen? User LED 0 is going to RD4. So RD4, if you keep it high, then what will happen? It will block. So the LED will not glow. And as soon as you make it low, so it will find a path and it will start glowing. Understood? So to make this RD0 of RD4 and RD5 low, you have to pull the port pin low or the microcontroller pin low. Got it? Similarly, another method of connecting the LEDs like this. So let us say I have user LED2 which is connected here, user LED2 which is connected to RD6. So as soon as RD6 is low, it won't glow because there is no power that is going here. Now as soon as it becomes high, what will happen? This high will make it glow. Similar to that, user LED3 will also glow high by making the port pin high. Got it? So to glow these two LEDs, you have to keep port pins low. You have to when you want to glow these two LEDs, you have to make port pins high. Got it? Now sometimes what happens is very powerful LEDs are used, okay, which require, let's say, 50 milliamperes or like 20 milliamperes or something like that. So you don't want to waste your port pins and draw that high amount of current, okay. So this is very good method to connect those high power LEDs where you require a lot of current, okay. So what I have done is I have put one N channel MOSFET, okay, N channel MOSFET, and user LED 5, you can see user LED 5 is connected here, okay. So it is going to RE1. What will happen? As soon as RE1 goes high, this MOSFET will get switched on. So from drain to source there will be a current connection, okay, current path flowing. And as this connection made, then this LED will start glowing. Got it? So till the time this user LED 5 pin is low, this is open, and once this is open, so drain source, the path is not complete, so LED will not glow, and as soon as you make it high, it will start glowing. So this is another way to connect LEDs, okay. So same way you can use user LED 4 as well. So we have completed power supply. Then we have completed push buttons and dip switches. Then we have completed our LED connections using 3 methods, okay. Like the port pin as a sink, this is acting as a sink, okay. This is most preferred method, okay, if you require very less amount of current. And this is acting as a source, like port pin, microcontroller port pin will be acting as a source, okay. And here in this case, microcontroller pin is acting as a driver, okay. Understood? Now let us see some other various applications for this particular microcontroller. So what I have done is I have used one temperature sensor, okay, so with I2C and SM bus interface, okay. So this particular temperature sensor, let me make it little bigger and you will be able to see it properly. So this particular temperature sensor, what it is doing is it has I2C connection like I2C SDA and I2C SCL, and once you connect it to the microcontroller I2C interface, what happens? This particular temperature sensor finds the temperature of the device where it is connected, okay. And as soon as it finds, let's say you have set this I2C pin below, like let's say 50 degrees centigrade. So as soon as the temperature goes beyond below, like more than this, okay, more than this 50 degrees centigrade, then this alarm will go low, okay. So this is pulled high, and the microcontroller pin, alarm pin, is pulled high. Now as soon as it goes low, because the temperature has found out that it is more than 50 degrees centigrade, then it becomes low. And as soon as it becomes low, you will be able to take some action. So it is kind of acting as a alarm. So this particular temperature sensor can give you alarm based on the temperature that it has been detected, or the temperature threshold temperature that you have made it. So LM73 is one of the best temperature sensor for keeping an alarm. So these are basically used in your industrial applications or maybe home appliances where you need some alarms, and based on that you will be taking an action like switching down the shut down the device unless the temperature goes below a threshold value. This address pin you want, you can connect it to microcontroller pin, address pin. Okay, so you can keep it low or high. So this, in this way you can be able to connect 2 or 3 devices together. Okay, and if you don't want to waste one of the port pin, you can directly keep it connected high, and this is how by default it will be high. So one of the device is acting as a for high, and another device, if you want, you can keep it low, like pull it down, so that will be acting as another device. Okay, so in this way 2 device you will be able to utilize. So if you have any doubt still in this particular temperature sensors and how you can utilize this particular temperature sensor for your alarm application based on the machine that you are using, and it getting heated up beyond that particular temperature, you want to take up some action, so you can utilize this. All right, so in this session actually we will see a lot of temperature sensors. We have some more. Let us say we want to find out what is my analog sensor value. Okay, so one of the very good temperature sensor from microchip technology. Okay, microchip technology. So this is my TC1047. Okay, so in this you can see that we have VDD 3.3 volt, you can give it. We have just one ground pin, another pin is your output. So output pin is very easy. You can take 10 millivolt per degree centigrade. Okay, so there will be a rise of 10 millivolt per degree centigrade. So you can see from the graph, this is taken from the data sheet. Let us say it is giving you zero point 0.1 volt, that is 100 millivolt at minus 40 degree centigrade. Now minus 20 degree centigrade, that is 20-degree rise. So in 20-degree rise, the total difference is how much? 1 to 3. So 300 millivolt. Okay. So from minus 20 to minus 40 to minus 20, it is how much? 200 millivolt difference. So 200 divided by 20, that is 10 millivolt per degree centigrade. So in 1 degree centigrade rise, there will be a difference of 10 millivolt output. Okay. So let us say any place, let's say you have a temperature value of 40 degree centigrade. So what will be the value that you will be reading at the output? 0.9 volt. Okay. So you will see 9 volt here. Let us say you have read 60 degree centigrade, then you will be seeing 1.1 volt. Okay. So this is how you will be able to decide based on the uh, value that you have read it on your ADC. So this temperature out one, you can connect it to one of the ADC line. All right. So I have given you all these applications and how we can connect it to our microcontroller pin, that we can summarize at later. If you want to reduce the cost with the same IC, like SOT23 only, you can go ahead with uh, this Texas Instrument IC. So this is my this is the temperature sensor from Texas Instrument, same SOT23 package, and it is also same 10 millivolt per degree centigrade resolution. All right, so it will also give you 10 millivolt output per degree centigrade. And if you want to see it transfer characteristics, so transfer characteristic, you can see that at minus 40 degree centigrade, this is taken from the Texas Instruments data sheet, TMP 235. This is the part number TMP 235. Okay, so you can see at minus 40 degree centigrade, if it is the temperature, then you will see at the output 100 millivolt. Actual output is also 100 millivolt. Okay. Similarly, if you keep on going, like let's say 40 degree centigrade, then you will see 0.9 volt or 900 millivolt. Okay. Similar to that, if you go like 60 degree centigrade, you will see 1.1 volt or 1.1 volt in linear wise, that is actual value. So you can see the microchip that is reading from minus 40 degree to 125 degree. Similar to that, Texas Instrument is also reading from minus 40 degree to actually it is going up to 140, 150 degree centigrade. So at 150 degree centigrade, you will see 2 volt reading. Okay. Now sometimes what is happening is this particular IC, that is SOT23 package, is not available readily. Okay. Because it is in very high demand. All right. Because of its high dissipation capacity as well. So generally people are going for like SC70 packages, which is 6 pin package. Okay, so they are very abundantly available. So you can see that also I have given you here TMP 235A2D. Okay, CKR. So DCKR is the complete part number for SC70 package, and for SOT23 package, A2D BZR is the complete part number. Got it? So you can see only 3 pins are used. One is VDD, which is power pin. One is V output. So output you will see exactly equal to your SOT23 package, device, and your ground. And rest 2 pins are extra pins, which are actually not connected, no connection pin. Okay. One more good thing that I wanted to tell you, directly you are getting output here. Okay, and you can read it to the ADC pin and see what is the value. All right, the analog value. Now if you want to make it much more sturdy, much more reliable, and much more better noise free, then you can send this to a buffer, and in through this buffer you can read to your ADC. So instead of reading directly from here, you can read it from here. Okay, and send it to one of the pin which is capable of reading the ADC values. Got it? So guys, I think you guys are fine with all these peripherals, like how to connect them, how to do this. Let me tell you one more interface which is going to be EEPROM, which is very very versatile. Everybody tries to use them. Okay, so this is the EEPROM 4 KB EEPROM taken from Microchip. Okay, MIC Microchip technology. So this is 4 kilobits EEPROM. I have by default made it like write protection is if you put it ground, then it will be not protected, like it you are allowed to write it. Okay, and A1 A2 are address lines, and this is VSS is ground. So all of them I have grounded, so one of the configuration I am using. Now if you want to use more of this particular EEPROMs, so you can keep changing this A1 to like high and A2 low, something like that. So you will be able to use a combination of how many, like A1 A2, two pins are there, so 0001 1011. So total up to 4 devices you can utilize. Okay, based on this particular configuration of address lines. And this is the I2C lines, like SCL and SDA, that is clock line and data line. So you connect it to I2C SCL and I2C data line of your microcontroller. So this is how you will be able to interface your EEPROM with your microcontroller. All right, and the power pin, it can take up to 5 volts, so it is very easy to communicate with that particular microcontroller. Understood? Let us say one more connection, which is RTC clock. Okay, so real time clock, generally people you try to like utilize outside, because the particular microcontroller may not be having RTC, inbuilt RTC. So this is a particular device which is DS1307 plus, and it is taken from Maxim Integrated. Okay, Maxim Integrated, very good device, very sturdy device, very much useful. And it has also a communication like interface of I2C SCL and I2C SDA. So this has been pulled with 10 kilo ohm pull up resistors, and SCL and SDA are connected. Now it requires one power which is 5 volt connected, and it is output which is need not be connected, so it has been left out. It requires some power. Okay, so that is VBAT power. So let's say this 5 volt is not connected, at that time VBAT will be keep on supplying. Okay, so this VBAT power 3 volt is a coin cell. So coin cell you can connect it here, and it requires one external oscillator, so that is X1 OSC and X2 OSC, that is connected to 32 kilohertz crystal oscillator. Okay, so 32.768 kilohertz crystal oscillator is connected through this. Got it? If you want the exact part number of this particular and these two exact values of the capacitors, you shall be able to put down your comments in the comment box, or there is a questions, I shall be able to give you exact part number for your particular applications. Okay, so it is very easy to design. I'm giving you a rough sketch of how you can approach for designing your RTC interface through I2C lines across a microcontroller. Got it? Earlier also I had talked about lot of temperature sensors. So one of the very sturdy temperature sensor which is used generally, earlier I talked about the SMD components, which was SOT23 package. This is through hole component TO92 package. Okay, and this is very very sturdy. This is very much useful in our thermometer applications as well. Okay, so you want you can just give your 5 volt up, power and ground it, and take your output just like that. And same way, your TMP 235 was there. It is also capable of giving you very good output. Okay, so if you want, you can see the data sheet of LM35 CAZ and see the transfer values, like what is the value at minus 40 degree centigrade, what is the value at minus 30 degree centigrade, like that up to 150 degree centigrade. It will give you the particular values of your outputs. All right, and connect it directly to a ADC pin. So this RE2, if you go ahead in your microcontroller, you will see this is capable of ADC connection. Okay. Now, let us say we require, like buzzers or beep sounds or something like that based on some alarms or something. Okay. So for that, I have used one of the very good magnetic buzzer transducer that is taken from CUI. Okay. So there is CUI devices company, which is very good company. So the part number for this particular buzzer is CST 951 AP. So 951 is actually 5 volt and 931 AP will be 3.3 volt. Okay, so if you want to use a 3.3 volt application, you have to go for CST 931. Okay, and if you want to use for 5 volt application, you have to go ahead with CST 951 AP. And instead of connector here, you can directly put this uh, buzzer. Okay, so I've not given here buzzer symbol. You can directly connect your buzzer symbol here. Now how it is working? So I have given a provision of resistor as well, because some of the magnetic resistor, magnetic buzzer is there, so that will require your diode, but some other buzzers require resistor. Okay, so for that you don't have to design another circuit. So I have given a provision and I have made it not used. Now what will happen? This is actually 2.7 kilohertz magnetic transducer. So here you have to give a PWM, okay, PWM of 2.7 kilohertz output. So at RE0 you have to give a 2.7 kilohertz PWM signal, and this PWM signal will make it connected, disconnected, something like that, and this is how it will start giving you a beep. Okay, so till the time you have to keep your beep sound on, you keep giving your 2.7 kilohertz PWM signal, and as soon as you don't need the beep sound, you have to switch it off. All right, all right. So when you need the particular code or something like that for PWM, and how you can generate, let's say 10 beeps you want whenever alarm happens. So 10 times you can keep giving this PWM after a delay, like let's say some 200 millisecond or 1 second delay, you can give the PWM. So this is very simple connection. You have the part number of your buzzer, you have the part number for your diode, you have the part number for your uh, transistor like BC847 CW. If you want, you can use here MOSFET as well. Okay, so like BSS 138 is one of the very general, very sturdy MOSFET that you can utilize it. All right. Now, very versatile application is one of the more application is IR sensor application. Okay, so IR sensor application, what I have done is this is 3 pin IR sensor application, IR sensor which is taken from Visa. Okay, so Visa is one of the best company. Visa is one of the best company for your sensor applications. Even some other parts are also there, like resistor, capacitor, inductors. So many things are there with Visa. but I see sensors are like one of the best portfolio with Vision. So if you have some remote, like infrared remote control systems, you can directly connect these two pins. So you have a VCC pin, which is 5 volt taken, okay, and the output is directly going to your interrupt, okay. So you can see IR sensor has been, uh, like got it. So you can see your IR sensor is detected. So whenever you press the button, this IR sensor will be detected. So very simple application, just 3 pin connection. Output you can send it to your microcontroller pin. So whenever there will be a like button pressed or something like that, this IR sensor will send a signal, and this signal will be received by the microcontroller interrupt pin RB0, and that RB0 will makes your whatever action that has to be taken based on this IR sensor input, that will be taken care. Okay. Now, very important thing is ADCs. All right. So what happens is ADCs is this. Let's say you had VDD, right, which was actually 5 volt. So what I have done is VDD I have taken here, and I have taken a resistor combination here, voltage division, and this voltage division, what it is doing, 3 volt and 2 volt. So basically it is 2 volt. If it is 5 volt, it will be having 2 volt here. So this 2 volt after this what do you say, buffer, it is going to RA0, which is going to be your ADC. Got it? Similar to that, I have taken another signals. Let's say ADC3, some ADC0 somewhere it is coming, and after buffer I am taking sending it to RA1. Similar to that, ADC3, which may be already buffered, directly I am saying it sending it to RA0. Okay, RA2. Sorry. So RA0, RA1, and RA2, three ADC pins are used for your ADC conversion. So I will show you like from where ADC0 and ADC3 are coming. So this is an external connector which is connected. So ADC0 has to be like measured, and ADC3 has to be measured from this particular device from where it is coming. Okay. And there are some signal like enable signal. You want to enable some of the device in outside some board, so you can send from your microcontroller like high, so that that device can get enabled. Suppose you want to like see whether that is switched on or switched off or not, so that particular device will send a signal, and based on this you can read this particular on off signal to your microcontroller, and here you will be able to decide that the device has been switched on or off or not. So this is how actually you put your like interfaces between one board to another board. Got it? And the best thing what I have done is I have sent this power also to the other board like VDD power and the ground, so that if that board is not having power from this VDD, that board can take power. Got it? Now, very last thing what we'll do is we'll try to understand how we can interface LCDs. Okay. So this particular LCD, acha, one more thing before that. Uh, this particular connector, either you can have a housing connector like this, okay. So this part number I have already given 68800 611 okay. Or otherwise you want, you can have a this header kind of thing. So this header 61300 61121. Got it? Both of the part numbers are from Worth Electronics. So I prefer Worth Electronics because they are very friendly, okay. And even cost wise, you can say that you can compare that they are a bit lower cost compared to Molex or Harwin or Semtech or some other like connector companies like, let's say, JST America, okay. So many other companies are there. So I'll suggest you to utilize your Worth Electronics devices. Worth Electronics is one of the best company for your connector application and even EMI devices, okay. Now let us see LCD interface. So I have taken 16 cross to like character LCD, and instead of using your RC0 to RC2 and RD0 to RD7 for other peripherals like push button LEDs and all, you can disconnect them or you can remove them and utilize them for your LCD. So only one of them you can use. Either you can use LEDs or like push buttons or something like that, or otherwise you have to adjust them for to some other port pins. Okay, so RD0 I have used because they have the capacity of data communication. Okay, so what is happening? As you can see here, let me make it little big. As you can see here, that you have RS pin, RW pin, like read write pin, and then enable pin. So these three pins has been connected to your RC0, RC1, and RC2 of the microcontroller. Next, data pin 0 to data pin 7 are connected to RD0 to RD7. These are parallel data bus lines. Okay, and now you have one anode which is going to a like power pin. So VDD is connected to the anode through a 1 kilo ohm resistor. So this will be powering this up. Okay, another one is like VO. So basically it is kind of contrast setting. Okay, so contrast setting is connected through the VDD pin and through a pot, like like one variable resistor. So based on that you can set your contrast of the LEDs. And this VDD is your supply, and VDD VSS is your supply. So they are connected to the LCD by a 10 microfarad capacitor and 0.1 microfarad capacitor. One more, this cathode, if you want, you can like enable this through your microcontroller. Like once RE1 goes high, what will happen? This particular transistor will get like conducting, and it will short the cathode. All right, so based on the requirement you can utilize this particular one. Or what you can do is, by default you can keep one resistor here and make it 0 ohm, not used. Okay, so if you do not want to utilize your one of the port pin for this particular job, you can directly make it utilized, and your cathode will get grounded. All right. So hope you guys are okay with this particular like complete peripherals understanding about uh, PIC 16F 18877 I P 40 pin PD package. So this 40 pin PD package as well as 44 pin uh, TQFP, TQFP. Okay, so both will be almost same. Okay, so you can utilize them as long as you want. And if you have any doubt regarding the adjustment of the port pins for your particular like peripherals, like how do you want to adjust which pin to be connected, which pin not to be connected, I think one more point I have not told you guys, that this RA4 is pulled up. Okay, so this is pulled up by default because it is a open drain pin. Okay, open drain pin. So if you have a microcontroller pin open drain, then the output cannot be high unless you pull it high. So if it is being used for output, okay, output, then for that purpose what you have to do is you have to pull it high, and then only RF4 will be high whenever you make the microcontroller pin high. Got it? This is how. So let me give you the complete circuit. So this is the complete circuit. Let's say this is my microcontroller connected here, and this is our power supply connected here, this is our LCD connected here. Okay, and this is our push buttons, this is dip switches. So I am reducing the number of dip switches because I have to use them for another purposes. So based on your convenience, based on your requirement, you can keep changing. Okay, I have removed the other LEDs so that I can utilize those LEDs port pins for other works. Okay, this is our external MCU connector. Okay, this is our what do you say, buzzer. So I told you for for your 5 volt application you have to change the part number to CST 951 AP. Got it? So this is how you will be able to utilize them. Understood? Similar to that, this is my IR sensor, this is my RTC application. Okay, and this is my EEPROM application. So only one of them you will be able to utilize, because let's say you want to use RTC application. So rest other devices I have put 0 ohm here, 0 ohm resistor here. So what you can do, this 0 ohm you can disconnect, so that this particular EEPROM you won't be able to use. So any one of the applications you will be able to use. I'll give you a method. Let's say, let me tell you again first. Here also there is like I2C is there. So if you want to use this also, and this as well. Okay, so for that I'll give you a method in my next video, how we can utilize all these three, or maybe even more than these three I2C lines in a single MCU line by using switches. Okay, so I'll be using a switch application, and that switch will be able to like multiplexer switch will be able to make utilize all of them. Okay, this was my temperature sensors. Okay, so all right guys, I hope I'm able to clarify the complete understanding of PIC 16F 18877, very powerful microcontroller from Microchip. Okay, so this particular microcontroller is very much used in college applications or even automotive application. Okay, because of its sturdiness and its robustness and its very strong device. Okay, so if you do have any questions or any understanding that you want to have, you put your questions in the comment box, and I shall be able to give you your question answered as soon as possible. Thank you so much.